Can I be heard now?
Yes, you can, finally.
Okay, all right.
So I leave you the... Please go ahead, and thank you for giving us your time.
Thank you very much for attending this webinar on vestibular evoked myogenic potentials. Thank you to Professors Solara Sinau and Afghal Mohammed for arranging this symposium, if you like, of presentations. So there are 2 lectures scheduled for today. This lecture that I'm giving now is related to vestibular evoked myogenic potentials, how they are done, and the reasoning behind how they are able to record from the vestibular system. So this slide is for the benefits of those participants who are not in the ENT field. So the vestibular system, as most of us know, is responsible for the sensation of balance. We have the end organs or receptors of the vestibular system located in the inner ear. 2 sets of end organs are present: the semicircular canals that are responsible for detecting angular acceleration, and the otolith organs, the saccule and the utricle, responsible for linear acceleration. And when we are talking about vestibular evoked myogenic potentials, we are referring specifically to the otolith organs and recording function from these end organ receptors and their pathway through the peripheral and central nervous system. So evoked potentials, as you know, require a consistent stimulus to be given, like, for example, visually evoked potentials, brainstem, auditory evoked potentials, etc., etc. For vestibular evoked myogenic potentials, the original stimulus used when designing these evoked potentials were to use a physiological or natural stimulus to create head acceleration, and that was to place the patients in rotating chairs or allow the head to drop from a lying down position. But as you can understand from this description, that these examinations were difficult for the patient, not very reproducible between trials, and produced potentials that were of long latency. We now have at our disposal vestibular evoked myogenic potentials, which are easier to perform, at least easier than placing a patient in a rotating chair. And in this case, we use sound stimulation. How is it possible to use sound stimulation? This will be described in the next slide or 2. So this examination was around from the 1990s and has developed since then. And unlike the standard sensory evoked potentials that I mentioned earlier, the vestibular evoked myogenic potential is recorded from muscle, tonically contracting or tonically active muscle. But this remains a non-invasive method. Everything is done from the skin surface, but this evoked potential is specific to the vestibular system. And the stimulus used in vestibular evoked potentials, vestibular evoked myogenic potentials, in the majority of cases, if you have it on your system, is tone stimulation, not click. If you are familiar with brainstem evoked potentials, although you can use clicks. Tone stimulation is the best form of sound stimulation to stimulate the vestibular system in the ear, preferably at 500 hertz. And you also need a stimulus of 120 decibels above peak sound pressure level, which is equivalent to 90 decibels above average hearing threshold. You can use bone conducted vibration, although you need to at least use air conducted sound and bone conducted vibration in addition to the air conducted sound. Electrical stimulation across the mastoids is also possible, but is more technically difficult to perform, and only a few laboratories do it nowadays. The majority of laboratories use air conducted sound using headphones, but bone conducted vibration can be used as well. Now, how is it possible for sound stimulation to stimulate a system responsible for the sensation of balance? Well, as you can see here, we have a picture of the ear with the middle ear here, and the inner ear with the perilymph and the endolymph, the cochlea to one side, and the vestibular end organs located here in the vestibule in the semicircular canal. Normally, when sound transmits from the middle ear ossicles into the inner ear, sound waves immediately move laterally. And that's why the cochlea is located to one side. The fact that the cochlea is located to one side of the inner ear is not by chance. Sound waves naturally diffract and move laterally when going from solid to liquid. But with the right kind of sound, the right frequency and the right intensity, before the sound waves move laterally, they will move forward, creating sound waves in the perilymph, changes in the membrane of the otolith organs, sound waves or pressure waves in the endolymph, and move the hair cells in the otolith end organs and send evoked potentials down the vestibular nerves. So this is the principle of how sound stimulation can be used to stimulate the vestibular system. And one of the many advantages of using vestibular myogenic potentials, especially if you are in the ENT field, is that you can record separately from the superior and inferior vestibular nerve. The vestibular nerve is composed of two parts, a superior part, an inferior part, and there are some conditions, especially in vestibular neuritis, that can affect either one or the other. So it's important to have parametric examinations that can selectively stimulate or record from each of these individual vestibular nerves. And something that will also interest the neurology field and neurophysiology is that using this examination can also allow you to determine if there is any lesion in the brainstem up to the midbrain and also down towards the spinal cord, and even including the upper part of the spinal cord. So, like I said before, with regards to the stimulus, the preferable stimulus is tone stimulation at 500 Hertz and at 90 decibels above average hearing threshold. Some systems, though, do not have tone stimulation, especially if you perform brainstem auditive evoked potentials in your laboratory. You may only have clicks available. You can do VEMPs with clicks, but you need a stronger stimulus. You need to go to at least 100, 110 decibels above average hearing threshold to get a good response. And you need to average from 100 to 200 stimulations, 100 to 250 stimulations need to be averaged. In the majority of cases, 100 can be enough. So we have two types of vestibular evoked myogenic potentials at our disposal. The first I'm describing here now was the first that was discovered from 1990 onwards, and this is the cervical vestibular evoked myogenic potential. The cervical vestibular evoked myogenic potential is recorded from the tonically active sternocleidomastoid muscle on the same side as the ear being stimulated. And this examination, the cervical vestibular evoked myogenic potential, records function from the saccule, mainly saccule, because there is some utricular activation as well, but it's mainly a saccular response. From the inferior vestibular nerve, the vestibular nuclear complex in the brainstem, the medial vestibular spinal tract, motor nucleus of the sternocleidomastoid muscle, and the upper part of the spinal cord. I mention these structures as well because I'm sure there are participants here who are maybe in the neurology field and neurophysiology field. It's important to know that this pathway also includes this central nervous system structures. And the response that we record is mainly an inhibitory one, which I will describe in more detail very soon. So the setup to record vestibular evoked myogenic potentials or cervical vestibular evoked myogenic potentials is simple. Like I said, everything is from the surface, from the skin surface. The active electrode is placed on the middle of the sternocleidomastoid muscle. So you locate the sternocleidomastoid muscle, usually by asking the patient from a lying down position to lift their head up from the pillow, and you can see it in most cases, or you can at least feel it below the skin if the patient has a fat neck. So the active electrode is placed on the middle or in the upper 1/3, but usually in the middle. The reference electrode is placed on the clavicle and the ground, either on the forehead or on the sternum. It doesn't matter where, as long as it's near the head. This setup is what is used by those who work in the field. The majority of those working in the field using this setup. There are publications that use alternative setups with regards to electrode positions. Why? And there are some cases where I don't understand why they use a different setup. This setup is the best setup to record cervical vestibular evoked myogenic potentials. One of the main reasons for this is to make sure that the reference electrode is as inactive as possible, so we are not recording from potentials from other parts of the face, and also so as not to record potentials from the other side, because even though we are recording from the ipsilateral sternocleidomastoid muscle, there are contralateral responses which are usually inverted, and instead of coming from the saccule are believed to come from the utricle. So to obtain a clear, predominantly saccular response that you can rely on and you know where the origin is from, the best place to place the reference electrode is on the clavicle on the same side. And to obtain the cervical vestibular evoked myogenic potential, one asks the patient to contract the muscle at the same time as you are giving the sound stimulation. The reason that you need to contract the muscle, like I said earlier in an earlier slide, this is an inhibitory response. So the response appears as a transient, very transient inhibition of muscle contraction, which I will show you soon. The best way to contract the muscle, where you get the largest responses, is by lifting the head up from the pillow while the patient is in a supine position or lying down position. You can have the patient, if you do not have room in your lab and you only have room for chairs, to turn the head to the contralateral side against resistance. Do not ask the patient just to turn the head. You need to have some resistance so you can have an adequate amount of contraction of the sternocleidomastoid muscle. You can do this, although the responses are reported to be smaller than by lifting the head up from the pillow. So if you can have the patient lying down, you will get better responses. So the first waveform that you see here at the top is a typical example of a cervical vestibular evoked myogenic potential. You have the contracting muscle, the sternocleidomastoid muscle in the background, and when the sound or the activation of the vestibular system reaches the sternocleidomastoid muscle, there is a very transient inhibition, and then the EMG of the sternocleidomastoid muscle resumes. And this transient inhibition, which is a positivity, occurs at around 13 milliseconds after stimulus onset, followed by a negativity at around 23 milliseconds. So this is a waveform that you will get in the majority of cases. There will be some patients that produce a lot of EMG, and it may be difficult to see on occasion, but it's very important, at least in all possibilities or in all occasions, you should at least anyway obtain more than one trace. So more than one trace, even in difficult situations, when you superimpose two or more traces, you will see a transient inhibition, even in a greater EMG background. Now, what's important at this point is that we are talking here about muscle contraction. One of the phenomena associated with the VEMP is that the stronger the contraction, the larger the response. Therefore, if you do not control the contraction of the muscle somehow, and one patient after the other contracts the sternocleidomastoid muscle, how they feel that it should be contracted, even though you are watching it, your amplitudes will be very variable and your standard deviations will be very large, and you will not be able to place your lower and upper limits of normal. So you need to control or normalize for muscle contraction. I don't have time here to go into the various ways of doing this. There are various ways you can do it depending on the system that you have. And at this point, I'd like to say that at the end, on my final slide, I will give you my email. If you have any questions or you don't have time to ask me anything here, you can send them to my email and I'll be very happy to help. If you want a PDF copy of this presentation, I do not mind, I can send you that as well. So anything with regards to this presentation, whether you have questions or you want a PDF file of this slide presentation, drop me an email and I can send them to you, no problem. Now, what I'm showing you here in the bottom is a almost simultaneous recording of the EMG. So I am recording here EMG from the sternocleidomastoid muscle without sound. The best way, and I'm describing the best way here, although like I said, there are other ways of doing this, the best way to control